Welcome to This Explainer. Let's just dive right into things today. When you look at the surface of North America, you aren't just looking at random piles of dirt and rocks. You're actually looking at a beautifully sculpted, almost ceramic-like masterpiece that has been fired in the kiln of deep time. Today, we're setting off on a continental expedition to decode the majestic mountain ranges of North America. We're going to uncover exactly how titanic geological forces forged everything, from the towering icy peaks up north all the way to the ancient, smoothed-out ridges in the east.
So, here's the roadmap for a journey today. First up, sculpting North America. Second, the Northern Giants. Third, the Rocky Mountain backbone. Fourth, blocks and volcanoes. And finally, number 5, the ancient Eastern elders.
Section 1. Sculpting North America. The tectonic kiln. Okay, to really understand these mountains, we have to start way down at the foundation. I want you to think of the earth beneath our feet as a colossal tectonic kiln. The sheer pressure and heat generated by shifting tectonic plates act as the primary forces that shape the topography of the entire continent. And here's a wild fun fact. These massive plates are actually crashing into each other at roughly the same speed your fingernails grow. It doesn't sound like much, but over millions of years, the results are literally monumental. Now, this kiln basically uses two main recipes to build mountains. First, we have folded mountains. Imagine taking a thick rug on a hardwood floor and pushing it together from both ends. It crumples and folds upward, right? That is exactly what happens when immense tectonic plates converge and crush together. Second, we have block mountains. These are formed not by folding, but by the Earth's crust actually fracturing and faulting. It causes colossal blocks of solid rock to be thrust upward, while other blocks drop down. So keep these two distinct forces in mind. They are the absolute secret behind the masterpieces we're about to explore.
Section 2. The Northern Giants. Towering ice and stone.
Let's move our expedition far to the north, up into the freezing, rugged landscapes of the Alaska Range and the Canadian Coast Mountains. This is where the highest, most formidable peaks of the continent literally pierce the sky. And the scale of the geography up here, it's honestly hard to wrap your head around until you hear the numbers. 6,194 meters, that is the staggering height of Mount Denali, located right there in the Alaska Range. Formerly known as Mount McKinley, Denali is the absolute undisputed king of the continent. It's the highest peak in all of North America. Standing totally in isolation, its towering icy peak represents the raw, upward thrust of the Earth's crust in this highly active northern region.
Now, shifting just slightly east over into the Canadian ranges, specifically the Coast and Mackenzie Mountain areas, we run into another monumental giant, Mount Logan. Standing majestically at 5,959 meters, it's the highest peak in Canada and the second highest in all of North America. Carved by just relentless glacial elements, Mount Logan is a massive testament to the freezing, slow-moving power of ice, acting on solid, uplifted rock. In fact, the glaciation here is so extreme that Mount Logan's ice fields are literally vast enough to create their own localized weather systems. No way, right? But it's absolutely true.
Section 3. The Rocky Mountain backbone. A continental spine.
Leaving the icy northern extremes behind, we're going to travel south along a continuous tectonic spine that basically dictates the entire climate and river flow of North America. We're talking about the legendary Rocky Mountains. They stretch for an unbelievable 4,800 kilometers. Originating from an event geologists call the Laramide orogeny, this staggering distance makes the Rockies the second longest mountain range in the entire world. It's this continuous, incredibly complex sequence of ridges, peaks, and intermountain plateaus that act as the Great Divide of the Americas.
So let's break down how this immense spine was actually built. The Rockies are a textbook classic example of folded mountains, and their story really kicks off in the late Cretaceous period. The really slow, violent, and continuous collision between the Pacific Oceanic Plate and the North American Continental Plate forced the Earth's sediment to fold and thrust upward. And crowning this vast folded landscape is Mount Elbert. Standing tall at 4,378 meters, it is the highest peak within the entire Rocky Mountain range.
Section 4. Blocks and volcanoes. The volatile West Coast.
Let's venture slightly further west from the Rockies to explore the geologically complex and frankly highly volatile edges of the Pacific Coast. This region is completely defined by the alpine sequence of mountain building, where the Earth's crust isn't just folding, it's snapping, faulting, and even melting. I want you to contrast the folded layers of the Rockies with the Sierra Nevada, which is this immense fault block mountain range. Instead of crumpling like that rug we talked about earlier, giant slabs of the Earth's crust just broke and tilted. And it's within this dramatic, blocky landscape that we find Mount Whitney. At 4,421 meters, Mount Whitney holds the title of the highest peak in the mainland contiguous United States. It's a jagged, abrupt landscape, entirely different from those rolling folds of the Rockies.
But here's the thing, the West Coast isn't just breaking apart, it's practically boiling. Running parallel to the coast is the Cascade Range, which gives us a very specific sequence of explosive volcanic peaks. Moving from north to south, we can trace a literal ring of fire. Glacier Peak, the towering Mount Rainier, the infamous Mount St. Helens, Mount Hood, and finally, Mount Shasta. Now, unlike the stationary rock blocks we just looked at, these are highly active volcanoes. They were born from the Pacific Plate subducting or diving beneath the American Plate, melting deep in the Earth's mantle and erupting violently right to the surface.
Which brings us to a really pivotal question for this explainer. We've seen the towering icy heights of Denali, the sharp broken blocks of Mount Whitney, and the explosive cones of the Cascades. So, if the western peaks are so massive, sharp, and rugged, why are the mountains on the eastern side of North America so much shorter and smoother? Well, the answer lies in the deep, deep past.
Section 5. The Ancient Eastern Elders, the Appalachian Mountains. To answer that question, we have to cross the vast, flat, intermediate plains of the continent, places like the Great Plains and the Canadian Shield, to visit the East Coast. Because over here, the story is completely different. Out west, we have the Alpine sequence. Those mountains are geologically young, highly energetic, super rugged, and full of active volcanoes. But on the east, we meet the ancient Eastern Elders, the Appalachian Mountains. These mountains have roots going all the way back to the Precambrian era. They are ancient, residual mountains. They've been subjected to literally millions upon millions of years of wind, rain, and ice. All that time has left them low, heavily eroded, and gently smoothed out. Let's look a little closer at the Appalachians. They are actually among the oldest mountains in the world. And what's truly mind-blowing is their connection to the Variscan orogeny. Geologists like the famous Alfred Wegener noted that the rock formations of the Appalachians perfectly match the ancient mountains of Western Europe. It's absolute proof that these continents were once fused together. In fact, here's a crazy piece of trivia for you. The Scottish Highlands and the American Appalachians are essentially the exact same ancient mountain range. They were just torn apart by the opening of the Atlantic Ocean. Today, the highest point remaining of this ancient range is Mount Mitchell. And because they are so incredibly old and covered in ancient fossilized swamps, they are incredibly rich in energy resources, specifically high-grade anthracite coal. Now, just because these mountains are ancient doesn't mean they aren't powerful today. Let's look at the eastern edge of the Appalachians, a feature known as the Fall Line. This is a very distinct topographic drop-off where the hard, ancient rocks of the mountains suddenly give way to the much softer coastal plains. As rivers flow over this southern edge, they create continuous waterfalls. Historically, and even right now today, these waterfalls have been harnessed to produce hydroelectricity. We are quite literally using ancient geology to power modern eastern cities. How cool is that?
Let's step back for a second and look at how all this builds together into a grand sequence. Because our tectonic kiln, it didn't fire everything all at once. Way back in the distant Precambrian era, the foundations of the Appalachians were laid. Moving forward through the Carboniferous and Permian periods, we see the Hercynian sequence shaping the east. Then fast forward to the Cretaceous period, and the massive Laramide orogeny folds the Rocky Mountains into existence. Finally, in the Pliocene epoch, the Alpine sequence sharpens the western coast, creating that rugged volcanic landscape we see today.
So if we were to hand out crowns across our continental expedition today, here's how the absolute highest peaks actually stack up. For the entire continent of North America, the Grand Crown goes to Mount Denali in the Alaska Range. Up in Canada specifically, it's Mount Logan. In the contiguous mainland U.S., the blocky Mount Whitney in the Sierra Nevada takes the prize. And finally, standing tallest within the massive Rocky Mountain range itself is Mount Elbert. Think of it as your perfect little cheat sheet for North American topography.
As we wrap up this explainer, I really want to leave you with this one thought. The mountains we see today, from the dizzying icy heights of Denali to the smoothed ancient ridges of the Appalachians, they are just a single frame in an ongoing million-year geological movie. The tectonic kiln is still firing. Those plates are still shifting, the volcanoes are still churning, and the rain is still eroding the rock. It really makes you wonder,
When the next frame of this movie plays out, what is North America going to look like in another million years? Keep exploring, keep questioning, and I'll see you in the next explainer.